Hello, welcome to our presentation on TestSmart, a tool for automated generation of effective test cases for smart contracts. This is a joint work from our team in the ICCKE department, University of Tehran. Smart contracts are immutable, verifiable, and autonomous pieces of code that can be deployed and ran on blockchain networks like Ethereum. Nowadays, many smart contracts are published on the Ethereum network for different applications, including security tokens, voting, gambling, NFTs, supply chains, insurance tech, property ownership, energy markets, and stock taking. But due to the immutability nature of blockchain, no change is possible on a deployed smart contract or a verified transaction. Hence, a buggy smart contract cannot be fixed even by its developers or owners. On the other hand, there are millions of dollars carried by smart contracts in the Ethereum blockchain, and a faulty smart contract may lead to an immense monetary loss. Unfortunately, there are more than 34,000 vulnerable smart contracts on the Ethereum blockchain, carrying a bit less than 5,000 of Ethers. As an example of famous vulnerable smart contracts, we can mention the DAO attack, which resulted in a loss of $150 million, or the parity 2 famous bugs that are multisig and accidental kill bugs have cost 30 and 300 millions of dollars respectively. So, guaranteeing the correctness of smart contracts has recently attracted researchers in software engineering and distributed computing fields. There have been several attempts to analyze the correctness of smart contracts. Most of these works focus on a static analysis of smart contracts based on known bug patterns. Although static analysis is a strong tool for evaluating software quality, it has its own limitations. First of all, this technique can only find the bugs matched with the known patterns. Also, since the static analysis methods do not execute the programs, there may be many false positive reports in the results. Therefore, static analysis techniques need to be strengthened with dynamic analysis methods such as testing. But one of the main challenges in testing is test design, which is the automatic generation of a sufficiently small subset of test cases that are more likely to find potential bugs. Several techniques have been discussed in the test community for both quantifying the effectiveness of test cases and automatic test case generation. For automatic test case generation, many approaches exist in the literature, including random test generation, symbolic execution, search-based algorithms, model-based methods, and fuzzing. Each one of these methods has some pros and cons, and they are beneficial in the appropriate use cases. On the other side, there are many published works on measuring the effectiveness of test cases. Some of these works use coverage criteria such as the statement, branch, or MCDC coverage to measure the test adequacy, while the others use mutation testing as a test adequacy metric. In this work, we fill the gap between test suite generation and test case selection by mutation testing by proposing our tool named TestSmart. First of all, we propose to use mutation testing as one of the most effective techniques for designing test adequacy metrics concerning fault revelation. Mutation testing modifies the source code of a program with tiny syntactic changes called mutation operators. For example, a simple mutation operator may change a mathematical operator to another one. To test the program, we should apply all mutation operators to the source code of the program, one after another, which results in a set of modified programs called mutants. To select a set of test cases from a pool of randomly generated scenarios, we should execute them on both the program and its mutants. If the output of the program and its mutant differ on the test case, we say the mutant is killed and the test case is selected. Otherwise, the mutant has been survived. Then, we propose our framework named TestSmart to fill the gap between test suite generation and test case generation by mutation testing. TestSmart takes a Solidity smart contract as an input and generates a test suite using an arbitrary test case generator. Also, it generates a set of mutants based on a list of regex-based mutation operators. Then, it selects a subset of the test suite along with a mutation score that shows its effectiveness for bug detection. Hence, TestSmart contains the following elements. 1. A tool for generating mutants. 2. A tool for automated generation of test cases. 3. A method for evaluating test cases based on the generated mutants. To evaluate our framework, we have implemented our prototype version using mutation operators from our previous work. This work conducted a comprehensive study on real-world known bugs for smart contracts and designed mutation operators based on these faults. It proposes 49 solidity-specific mutation operators in 10 classes that can reproduce 10 out of 15 famous solidity real-world most expensive bugs. This work also published a regex-based mutator tool by extending the universal mutator tool with these mutation operators. As regex-based tools are highly extensible for adding new mutation operators, TestSmart uses this tool as its engine for mutating smart contracts and generating lists of mutants. Also, we chose but are not limited to Manticore for automatically generating test suites and evaluating test cases based on the generated mutants in our prototype version. Manticore is an open-source dynamic symbolic execution tool that emulates the Ethereum virtual machine, symbolically representing transactions, storage, global values, and EVM's current state. Manticore also provides comprehensive APIs for developers to interact with it and even use this platform inside their toolchains. Finally, to check whether our generated test suite kills the generated mutants or not, we should compare the outputs for the original smart contract and the mutant on Manticore's emulated EVM. But the concept of output is different in smart contracts from the traditional software. Considering different parameters in smart contracts, we have identified outputs as the following parameters: transaction outputs, intermediate transaction and their results, balances of the Ethereum accounts, emitted events during the test scenarios, value of the global variables in the storage of the original smart contract and the mutant. Then, to evaluate the effectiveness of our prototype tool, we chose 4 smart contracts to generate the corresponding test suites. Our experimental results in the following table show that TestSmart can generate effective test suites for any Solidity smart contract using symbolic execution with a mutation score in the range of 50 to 100%. It also shows that the number of selected test cases can be significantly less than the number of test cases generated by Manticore. For example, in the first row, only 5 test cases are selected as effective from the set of 267 generated test cases. Additionally, these experiments show that the mutation score for test suites generated by symbolic execution depends on the usage of Solidity-specific syntaxes. More specifically, smart contracts that do not use Ethereum address, gas values, transfer function, cal mechanisms, etc. have higher mutation scores. We also evaluated the survived mutants manually, and in the following, we discuss mutants that are not killable by test cases generated by Manticore and the corresponding reason. First, we observe that Manticore does not concretize the symbolic values wisely. Therefore, the generated test suite may not kill the mutation operators which have been applied to the condition statements. Second, killing some mutants needs generating intermediate contracts. For example, to check an interface smart contract, we should develop a child contract inherited from the interface to implement the test scenario. Consider a function from the interface contract that is defined mistakenly as internal instead of private, which means it is accessible inside inherited smart contracts. Hence, the attack scenario needs an intermediate smart contract to access that specific function. Third, the Solidity compiler allows comparing Ethereum addresses with greater equal, lower equal, and other similar operators. But the Manticore only limits the address values to the contract owner and the attacker accounts. Hence, it cannot generate test suites that reveal the bugs in comparing Ethereum addresses. In this case, we recommend the Solidity compiler to statically analyze these statements before compilation and raise an error on using such operators on addresses. Last, in most applications, a smart contract needs the participation of many Ethereum users with different roles. For example, for an auction smart contract, we have many users as bidders and one user as the auction owner. Therefore, for killing some mutants, we need to design scenarios having multiple transactions, including auction start, bids from the bidders before applying the attack transaction. Eventually, as a conclusion, we proposed a tool chain named as TestSmart that automatically generates a set of effective test cases for Ethereum smart contracts. It consists of a module for test suit generation, a module for mutant generation, and one for test case selection based on mutants. As a prototype version, we used a powerful tool called Manticore for test suit generation. And for mutant generation, we have used an extension of Universal Mutator, which contains the mutation operators especially introduced for the Solidity smart contracts. Our results show that using this tool, developers can significantly reduce the size of the test suit and measure its effectiveness with a mutation score. Also, by analyzing the survived mutants, we have found the limitations of symbolic execution, especially for the Manticore tool, in finding bugs of smart contracts. In other words, we have shown what types of bugs may not be detected using the test case generation of Manticore. In conclusion, we believe that our framework can help Solidity developers and also testers to develop bug-free and safe smart contracts. Thank you for attending our presentation. Please do not hesitate to ask questions.